All right, so let's talk about relational databases. This is covering Chapter 2, Sections 1 through 4 in the Database Systems Concepts textbook. A database is a collection of tables. Now, tables is sort of the nice way to think about them. And you can basically think of a table like a sheet in a spreadsheet. So in an Excel, Excel with a spreadsheet, we could make a nice table. Well, that's what we're talking about. It's just like that, all right? We can also call a table a relation, okay? Each of our tables is going to have a name to them. And our tables have columns, which we can also, if we're talking, usually we'll talk about relations and attributes, or we'll talk about tables and columns. And then the tables have rows. So again, relations, attributes, tuples. And then a row represents a relationship between values. So here's a real simple example. Here's the users table, okay, or relation if we wanted to. It has attributes of ID, name, and email, and we've filled each row with values in that table, and there's a relationship between those values as represented by each of those rows. Now, this lecture is basically a lot of vocabulary for you to start to learn. It's going to help to read the book. Absolutely. Always helps to read the book to go along with what I'm telling you. Now, if we have a table, when we talk about basically a table in its abstract sense, it's just a relation. Okay, it's a relation, but when we talk about it that has a specific set of data in it, we call it an instance. So a table filled with a set of values is a relation instance. Now, just so you know, if we change any values or delete or add any rows, we have a different instance. So an instance is the complete set of all the data that we put in a table. And that's one instance. If we add a row, let's say a new user to the users table, that's a new instance of the relation, okay? This is all about definitions, and we got to learn some of these definitions. Now, we like to talk about the attributes. These are the columns, okay? So each attribute, so an example again is like the name, okay? Or the email. Each attribute has a set of allowed values. And since this is very mathematical, that's like saying, what is its domain? What are all of its possible values that it has? So an attribute has a set of possible values, and we call it the domain of the attribute. Now, we want to really, again, we've just talked about in the previous lecture about atomic actions. And now we're going to talk about atomic attributes. It's the word, we're using the word atomic in a similar fashion, but it's not the same thing. One is about data, one is about a series of actions, okay, that form then whether, again, whether multiple actions either happen or don't happen. They either all happen or they don't happen. That's the former one. We talk about transactions as being atomic. Now we're going to talk about an attribute. Is it an atomic attribute or not? Okay, so just because we're using the same word doesn't mean we're talking about the same thing. If we never take a value of an attribute and break it into smaller parts, we say that domain is atomic. And again, so this is atomic as in like an atom. Oh, it's its smallest possible unit of matter. Of course, let's ignore that we know that there are subatomic things, but the atom, atomic. And it's like, well, okay, wait a minute. This is highly abstract. Okay, so again, we had that table and we had a name attribute in it. So let's say we have a name like Fred Smith in there. And let's say we have a name in there like, Harish Chand. All right. So, we've got a common, the notion of a first name and a last name. And let's just draw this sort of table-like for us. Okay. So we have an attribute, so the attribute is the name attribute. And we've stored two values in, these are two separate rows. Now, if everywhere when we use data in our program, and again, we're going to be using this database to store data that our program needs, rather than storing it in a file, we're going to be storing it in the database. And so, yeah, let's say we have some list of names or something, and so we've got these guys and we're storing them in the database. Now, if we write methods or dealing with our database where we're like, I want to find all the Freds. And so then I start to always deal with or compute with like a first name versus a last name. And I always know that my notion of being able to tell first name from last name is that there's one space in between these characters that are part of these strings in here. Okay. I'm dealing with name actually as though it's composed of two things, a first name and a last name. I'm not really dealing with it and programming with it in an atomic fashion. I'm dealing with it in a non-atomic fashion. Now, this is a subtle example. A better example would be, let's say that you've gone, you see some sort of database and, someone makes you've got some notion of, let's say, a user ID, and then we say, favorite activities. I can't even, activities. All right. So we've got some table. And let's say they're going to store separate user IDs. So maybe this is user 23. And the favorite activities of user 23 are biking, hiking, sailing. And you could envision that maybe this is just simply a string that we like to display on a web page for a user. Okay, we're kind of treating that in an atomic fashion. We just read and write and we let the user write whatever they want. But if instead, what we often find ourselves doing is trying to find people who are biking fans versus sailing fans and other things, where we start to chop up this string and we're querying based upon the subparts of this string, So like basically we have a set or a list of things that we've stored into one attribute. That is not an atomic attribute because we're not using it in an atomic fashion. We're using subparts of that attribute. All right, that's what we need to know about atomic attributes. In general, just to say, look, don't store lists or sets in a single attribute. Just don't do it. Later we're going to find out there's all sorts of bad things about it. So don't do that. Always, you want attributes that are atomic, not attributes that you're trying to chop up. Okay? So, what else should we know? Well, one of the possible values in a database is null. And so we could set values in those rows. So a row for an attribute could have an actual value set to null. It's a special value in the databases. And nulls mean that we actually don't know what the value is, or it does not exist. And I'm just going to say right now that for the most part, avoid nulls. Don't plan to have a bunch of nulls in your database. I mean, this is day one of databases, and that's right. Avoid the nulls. Often we'll design databases and we're going to say things like, we're not going to allow nulls to go into the table because having nulls results in all sorts of strange behaviors when we end up trying to query these tables. So in general, don't allow nulls to go into your database. Don't incorporate them as part of your designs. We need to know about them. We need to be able to be aware of them, but we often don't want to purposely be using them, okay? Certainly not at the basic level. We want to try to avoid nulls. Okay. Then we have this notion that we can have a relation schema. This is a cool thing, but it's pretty simple, which is it is a table's name and its attributes. It actually could not be any simpler. Okay. So for example, and again, I'll say this again, we already said it, but a relation instance is when we fill up the table with data. Okay, so again, in an example, using what we had before, a schema, we would write it as users, ID, comma, name, comma, email. That's the schema. Pretty simple. What's the relation name or the table name? What are the column names? What are the attribute names? Great. And again, the instance is exactly the creation. We've got this table. We've got columns. And we have a bunch of data in it. That is one instance. If we change any of the data, we add any rows, delete any rows, we have a different instance of that relation. Okay. Keys. Whew. Let's talk about keys. Keys. It's important to know that when we want to talk about database design, but good database design relies on each row or tuple of a table relation being uniquely identified. Or uniquely identifiable. Okay, so all of those rows, we need a way for every single one of them to have a unique identity. This is so that we can retrieve specific rows of data from the database system. We don't always want all of the data, but we want to be able to obtain a subset of it. But in particular, we usually want to be able to talk about this row often maps to, in the real world, some specific sort of entity. So we could have, again, like that users table, a row is a user. All right, and we have to have some way of uniquely identifying that user so that we can refer to that user not only in that table, but in all other tables as well, okay, where we want to talk about users. Because we're not going to just have one table, one relation. We're going to have databases that are filled and created with lots of relations, and they're going to be interconnected, and they're going to share values across them that allow us to draw connections, relationships between these tables. Okay, so we need to talk about keys. Keys are how we identify. And you can think about keys if you go back to algorithms and data structures, and you've got, let's say, a hash table, and it's got a key and a value. You put the key in and you want to be able to retrieve the value. Or again, you might have, it's a dictionary basically. So you've got a key, I want to be able to get back out the value. Well, we always need a key to identify every single row in a table. All right. So what are some of the important definitions surrounding keys? Well, we'll start with super key. Sounds cool. It's super key. I guess it's supposed to be cool. Anyways, a super key is a set of attributes, and again, these are the columns, that allow us to uniquely identify a tuple, which is a row. Okay, so there's some set of them that if we look at the set of values that we have in a row for those attributes, those columns, we'll say no other row in that table for those attributes has those values. Across those attributes with whatever those values that row has, only that row will have that set of values for those attributes. Okay. Now we should note something here. Note a relation instance, which is basically, again, it's a table that's filled with data. Should not have any duplicate tuples in it. Okay. Thus, if we took all the columns or all the attributes as a set, we'd have a super key. So in other words, we're never going to have two rows in a table that have all of their attributes identical to each other. We'll never have two duplicate rows of data in a table. It's not allowed. It's not, and we just don't do that. Okay? So you could always form a super key from all the columns. But a super key is just simply defined to be a set of the columns, which we know that we could uniquely identify a row by. Relations or tables have lots of potential super keys. There's lots of potential choices between the columns that if we had those columns and knew what the values of a row were, that would uniquely identify that row. Okay? And because there are lots of super keys for a table, what we say then, we want to actually get to sort of a set of keys that we might really like to use. We don't just want any set of columns to uniquely identify a row, because we could always just use all of them. That seems highly inconvenient. Actually, we'd really like a very small set, or maybe just a single column that can be used to know as the key to uniquely identify a row. So what we want to do is we want to identify good possible keys. And so again, we want to identify good super keys that we could use to uniquely identify a row. And so we call these candidate keys, because we want to find good candidates that we'd like to use as a key. So a candidate key is a super key such that if we remove an attribute, and again, remember, a super key is composed of a set of attributes, it is no longer a super key, or no longer a key. Okay? So if we say, oh, we have these following columns, and they form a super key, but if we remove one of those columns and the remaining columns, we would actually find rows that have duplicate settings, duplicate values. We know that that set of columns is a candidate key. In other words, that's a minimal set of columns. We can't take away any one of those columns and still have a viable key that we could use to identify a row. That's a candidate key. Then we have this idea of a primary key. Now, a primary key is a single key that is selected by the database designer, that's you, by the way, from a set of candidate keys. And again, these are all the possible minimal keys that we could use. And another thing that we want the primary key, basically the primary key should never, so let's say a row's value for its primary key should never, or very rarely, change. Okay, so let's talk about this with an example. Let's say we're like an accounting firm, and so we have a table to keep track of our clients. So we have a table, and in it we've got the following columns. We have an ID column. We store their SIN. We also store the client's name. So this is the client's table or the client's relation. These are the columns. All right. Now, let's say our ID happens to be something that we've designed so that it's unique for each client. Okay. Now, we know very well that the SIN is unique So the social insurance number is unique for each person. But I want to mention something. You might not be aware of this, but I am as an immigrant to Canada, that when you first come to Canada and you come in on a work permit, you're given a temporary SIN. And then after you become a permanent resident, which I am now, you no longer have a temporary SIN, you have a permanent SIN. And your SIN changes. So it's unique for each person, but can change. And so if we wanted to refer to our clients elsewhere in the database by some unique identifier, the SIN actually would be a bad thing to use. Because again, we have this issue of, oh, geez, they changed their SIN. Now we have to find everywhere in the database where we use that SIN and update it for that client. If we instead, we've got this ID and we know it's unique for each client, and for the life of the client, it's unique, that's great. We'll never have to have it change, and we always have a way to identify that client. Okay, and likewise, again, we know the names can change as well. So if this is our table, okay, what are our super keys? So our super keys, again, are a set of columns that allow us to uniquely identify a row. Well, we know that ID by itself uniquely identifies a row, uniquely identifies a client. So it by itself is a super key. Great. We know the same is true for the SIN. It is a super key. It by itself can uniquely identify a row. Now, we could take the columns ID and SIN and have a super key. Well, I mean, if one of them uniquely identifies a row, both of them certainly uniquely identify a row, we'll never have a problem there. Likewise, we could take an ID and a name. That's a super key as well. No row will have both an ID and a name that is duplicate with another row. Again, because we know that ID is unique for every row. Name might not be, but because we could have two Fred Smiths. But you know what? Together, they will form a super key. And likewise, we can take our SIN and a name, and it's a super key. And as I said, we could take all of the rows, all of the columns, all of the attributes to form a super key. All right, so those are the super keys that we have in the table. Now, as a database designer, when we want to be able to talk about and to have, we eventually want to find a primary key that we could use. Then we want to be able to use and reference in other tables as well to refer to a client. So we want to say, what are our candidate keys? Okay, so if a candidate key happens to be, again, it's a super key that if we remove an attribute from it, it's no longer a key. So here, if we remove name, well, we're going to get an ID and a SIN. It's still a key. So we could remove name. We could remove SIN. Well, both ID and name are a key. So we could still uniquely identify things even if we remove the SIN. Or if we remove ID and we have just SIN and name, again, we'll still have a key. So this is not a candidate key. Could I remove name here? Yeah, I could, and I would still have a key. So this is not a candidate key. Same thing here. I could remove name, and we'd still have ID, and so it's not a candidate key. It's not a minimal key. We could remove something and still have keyness. Same thing goes here. We could remove ID or SIN, and the one that remains would still work as a unique key for the row, so that's not a candidate key. Well, if we remove SIN, we're left with nothing. If we remove ID, we're left with nothing. These are our candidate keys, okay? So these are the candidate keys for this table. Now, what should we pick as our primary key? So from the candidate keys, ID or SIN, which one has the property of less likely ever changing? It's this unique ID that we created for our client that is supposed to live for the life of the client. All right, so we would make this the primary, we'd make ID the primary key. We would not make the SIN the primary key. And again, the primary key means it's a key that we choose as the database designer to be the key that we want to uniquely identify the rows in our table. But it has to have the property of being a super key. It has to be able to uniquely identify a row, and we will want it certainly to have been a candidate key, so it's as minimal. All right, so if we have a primary key that is more than one attribute, this is known as a composite key. So if we have to use two attributes to form our primary key, it's a composite key. All right. There's one last thing to talk about quickly, or I guess maybe two things, and that is talking about this idea of foreign keys and also making schema diagrams. So let's say we have these relations, authors, ID, and name. And when we write out, so this is a schema. When we write out a schema and we identify the primary key, by convention, we underline it. So ID will be our primary key for authors. Books will have an ID. It'll be our primary key. We'll have a title. And in it here, we'll store an author ID. All right. Now, the author ID is going to be set to one of the IDs for one of the authors. So this is the author of this book, and we'll refer to it back here because we'll be using a matching ID in here. So we could have, so either way, this is what we call a foreign key. So this is a key that really that's a primary key in another table, okay? And we're sticking it here, and so it's a foreign key. All right. And so we can draw pictures, by the way, of and we can write out schema like this, but we can also draw nice pictures that help us see what's going on in a little bit more friendly fashion. We go ID, we underline it. We have a name. We can do books. We can have the ID. We can underline it. Title. Author ID. And what we can do is we'll draw connections between these tables. So we'll go from author ID to the ID to show that books is connected to the author table via the foreign key author ID, which refers to the ID. So for every book, we have one author. All right, now we might very well have an author who's authored multiple books, though. This is a very simple form of diagramming that we use early on in our talking about schema and tables in the databases. As we move on in the chapters, and eventually we get to entity relationship diagrams, we'll be much more formal about exactly how to draw diagrams. But this is a nice, easy way, and you'll see this in the chapter. And of course, we can have this as an example filled with real data. So if you wanted to, you could make, we could have an ID, we could have name, and we could have author, 1 be Bob, author 2 be Mary. This is our authors table, an actual instance filled with data. I have another table over here with, again, ID, title, author ID, and we could put in it here book 1, book 2. We could have the title hi, we could have the title by, and it just so happens that Mary, author ID 2, has written both hi and by. Okay, now that's the basics of foreign key. The book does talk about already, it introduces the idea of a foreign key constraint. And so let's put it this way. So based upon that example, if we require each row of books, so again, books is the table that has an ID, a title, and an author. So if we require each row of books to refer to a row in the authors table, this is called a foreign key constraint. Now you might be saying, well, of course we would. Why would the table says it's supposed to have an author ID? Well, you could envision, by the way, that we had that data that we just had, and let's say for whatever reason we've decided to delete an author. Now, any of the books that belong to that author in the books table would be in violation of a foreign key constraint if we required it. Okay, and so we could set up the database actually that it enforces this constraint so that we can't get rid of an author while that author still has any books in the books table. Likewise, if we have such a foreign key constraint, and let's say we allowed nulls into the system, you could have potentially envisioned someone trying to put in a book with a null author ID. But if we have a constraint in place that says it has to refer to something in the authors table, we would be in violation of that and we wouldn't be allowed to put that data in. So what we do is we end up designing databases with all these tables, and we end up putting constraints on them such that we're able to be sure that our data stays consistent. So that we don't end up putting things in strange and inconsistent states where we have books with author IDs but no such authors in the authors table. All right, so that's a real basic introduction to the first part of chapter 2 in the Database Systems Concepts book. Next, I'll end up talking about the latter half of that chapter where we talk about how are we actually going to query and get the data out of those tables. And we're first going to not talk about SQL, but we're going to end up talking about relational algebra, which is a nice introduction and a way to understand the mechanics, the sort of the math behind what SQL or SQL is designed to do for us to query relational database tables. All right,